Hi, everyone. I'm Daisy Hollman. I'm the program chair this year at CppCon, and also giving a talk. This talk is about expressing sameness in modern C++, particularly focused on implementation sameness, and I'll talk about what that means when we get into the talk. I also gave this talk at Core C++ in Israel this year, and I'm learning as of 15 minutes ago that it is very hard to give a talk and be the program chair at a conference like this. So if this one doesn't go well, there is a video of this talk being actually good. And you can look that up on YouTube. I also had a little bit more time there, so I got to get into some of the things in a little more depth. It's very unlikely that I'll say things exactly the same way, so if you're watching this on YouTube and you really don't understand it this time through, feel free to go over to that one and see if that helps, and then if not, send me an email. I'm happy to talk about these things. This is something that is really important to me, and something that I really like talking about in terms of the way that C++ is evolving. A few disclaimers to this talk. So I'm pretty scared. I don't usually give software engineering talks in the past few years. Any of you have seen my talks in the past few years. They've been about programming, and that even programming is a stretch. They've been more about stand-up comedy routines about C++ or something. They've been useful stand-up comedy routines, but this talk really is about software engineering, which means that if you disagree with me, I can't just go and push compile and be like, well, but it compiles. So that's hard for me to be open myself up to something that oh, someone actually smarter than me might disagree with me on this. But I think that it's actually important to say these things, and I even have some slides without code on them, which is really weird for me. I also want to say that it's really hard to talk about sameness and repetition in code that goes on slides, because in many recommendations, many engineering recommendations, the maximum amount of code that you should be comfortable with repeating is about the amount that fits onto a slide. It's somewhere between 5 and 25 lines or something like that, and putting more than that on a slide gets to be a mess, right? So think critically about the ideas that I'm presenting, and maybe not the exact code snippets or how you should do those code snippets in real code. Also, a disclaimer, I'm mostly interested in very large scale code that has to be maintained for a very long time. If you are in a competitive programming competition, don't listen to anything I'm saying, right? Just do it as fast as you can. Or if you're trying to hack something together that needs to be done by next week and then never used again, first of all, be absolutely sure it's never used again, because that's usually you're wrong about that. But secondly, don't worry about this, right? If that really is the case. This is about taking your time to thoroughly write high-quality code that can last a very long time. So there's a few common storylines in this. Code is written to be read by humans, right? If you are a professional software engineer, and especially if you're at this conference or watching this on YouTube, that means you care enough about C++ that you probably know multiple ways to write the same thing. Multiple ways to get the same assembly output, or essentially the same assembly output from your code. And your job as an engineer, not a programmer, is to choose between those, right? So code is meant to be read by humans, and you should think about code as the way of telling the reader something about what you're trying to do, right? You should always think of code in terms of how the reader will experience it. There's a fantastic talk on this from earlier in this conference. If you didn't get to go to it, go look it up on YouTube. Katie Roca gave a talk on thinking through how users will experience code as it ages. And I think that's a big driving factor behind how I think about code and how I think about software in this talk too. I'm also going to use the term cognitive load a lot, which is a fancy term. And but it's also a precise term that people use a lot when talking about programming languages, when talking about programming model design. And it's the mental effort that's required to understand and use code. So when you're writing real code, almost everything, like this long-lived code, almost everything you do should be focused on reducing cognitive load of the user, right? Like you're choosing between different ways of saying the same thing to the computer. Computers are very smart, right? We've spent a lot of time working on that. Compilers are very smart. As much as it seems they're not, they do a lot of things to generate the same code from different representations. That's what we talk about zero overhead abstractions or low overhead abstractions in C++. We're talking about the compiler's ability to get the same thing out of different ways of saying things. But humans don't work that way, right? You say different things, humans will get different impressions. So, and then the other thing that will come up quite a lot as I talk about this is information loss. So that's when the reader of the code doesn't have an easy way to retrieve a piece of information that's obvious to the writer of the code, right? So copy pasting is an example of this, right? When you copy and paste something in your code, the reader of your code does not know that the thing you copied from is where the thing that is connected in any way to the thing you pasted, right? You have lost information forever when you do that. I think there's this interesting thought experiment that I would love to do that would not actually work, but in general as a thought experiment, like what would code and programming languages look like if we disabled copy and paste in code editors? Like our languages would be much, much more expressive and much, much more efficient if no one in their day job for like a month was allowed to use copy and paste. So I mean, I want you to think about code that way as I start getting into this. Another way, if this motivates you better, is to think of copy and pasting code as selfish, right? It saves you time at the expense of someone else's time. You're robbing people in your future, in the future of your company, from understanding of the code that they have to then back out. Some non-themes of this talk. I don't care how long it takes you to type something. I really don't. And this discussion comes up a lot, and a lot of people disagree with me on this. I don't care. If you're typing most of the time you write code, you need a better development environment, right? You need something that's going to complete these things for you. Especially as we're starting to get into AI code assistance, right? The more that you write, the longer your variable name is, the more tokens your AI assistant has to gain context from, right? The more descriptive your name is of something, the better your comments are, the better that AI can help you, right? So it's not just other humans, right? It is for your own benefit also. And like the actual number of characters you type, I don't know if anyone's programmed with AI before, but you mostly spend your time mashing the tab key. And it does surprisingly well. I also don't care about adding a layer of abstraction within reason. This can obviously get out of hand. And again, the priority is readability. The priority is the experience that the person reading your code is going to have, right? If you don't know off the top of your head right now what the key binding to jump to the definition of a function, maybe, and ideally, actually, you don't know the key binding off the top of your head, your fingers are doing it, right? You can't even think of the key binding because you have to like do it with your fingers, then look at what your fingers did, right? That's how often you should be jumping back and forth between definitions and declarations, and that's how often you should be able to jump between layers of abstraction in your code, right? I also don't care about adding linear compilation costs within reason. This also depends on your organization, depends on your organization's needs. There are reasons why you may need to focus in on compilation cost. Distributed builds, caching, smaller files, modules. There's a lot of ways to improve compilation costs that don't come at the cost of developer productivity. But definitely beware of nonlinear compilation cost. And beware of using weird language features that can increase cognitive load, right? Both of those things are often lumped in with like, oh, I don't care how long the compiler takes. And then you look at the error messages that you get from the compilation, and you realize that you've used something that has made it very hard for someone else to maintain your code. So there's a separation there, right? We're always talking about making our code more readable. And I'm also not interested in making it faster for you to write code. I'm much more interested in reading and maintaining code. Code is read and maintained far, far, far more times than it is written. So here we go. Let's dive right in. So there's two different kinds of sameness that I want to break this topic up into for the purposes of this talk, and I think that it's a useful way of thinking about sameness in code. So interface sameness is having the same name for a function at the interface of your library, right? Where your users use your code, they have a name, and that name refers to different things depending on context, but the same way, right? Like polymorphism is an example of this. Traditional inheritance-based virtual polymorphism. Whereas implementation sameness is really about expressing that this chunk of code is the same for this thing and this thing, right? Or the way this happens is the same for this thing and this thing. Or the way this operates or the way this functions is the same, right? You're expressing this to the reader, not enabling the user, right? Importantly, interface sameness, once it is out in the wild, cannot be removed, or at least not very easily. You can't change your user's code. If you have a monorepo, you can do this. It is very, very hard. Even at Google, where we have some of the best people at doing this, it is not easy, right? Once you allow users to treat things the same way, it's very hard to change them to be different later, right? Whereas implementation sameness, you can change that at any point in time in the future when it stops becoming useful. If you need something to act differently, right, as long as it's not named the same thing in user code, you can make two different implementations for the two different names, right? Whereas, if it's named the same thing in user code, that is forever coupled. When done correctly, good interface sameness will lead to low code coupling, right? Whereas good implementation sameness will lead to high code cohesion, right? So if you look at like classical theories of software engineering, this goes back to like the 70s, talking about the differences between code coupling and code cohesion. And code coupling creates this unexpected sameness across different modules, between different modules in software. And code cohesion creates a sameness within a given module, right, that really expresses an understanding of why two things are the same or how two things are the same. So let's talk about the mechanisms that we have available to us in C++ for expressing sameness. Either implementation or interface. I'm going to get into which ones are used for what, and we'll go through it. And the first thing that obviously comes up is traditional polymorphism, right? This is what you get taught in undergrad. Who has used this recently? Like where you actually inherit and override a virtual function and you say, is A is a B? It is a lot fewer people. OK, maybe it's more people than I thought. But it is a lot fewer people than I think most undergrad CS professors would think. This is, right, it allows you to reuse to use different things in the same way, right? So if we say have a barnyard, which is our like collection of animals, right? And we put different kinds of animals, we can still loop over them in one loop and say speak to all of them, right? So notice that the code reuse here happens in the calling code primarily when you're talking about polymorphism like this. And traditional polymorphism is oriented around interface sameness, right? It can also be used for implementation sameness. Often that comes at the cost of a vtable and a virtual function call. But in general, right, this is what people think of first when they think of sameness. And hopefully by the time we get to the end of this talk, you won't think of things that way. The other thing people think of when they think of sameness in C++ is templates, right? So in the case of class templates here, like we have vector int and vector string, and they're expressing some implementation sameness without really coupling these two types, right? We are allowed to, the type vector of int and vector of string aren't really related to each other in any meaningful way, except for that they implement the same container for a different type, right? In this particular case, you're also expressing interface sameness, right? So a user who has used vector of int will have reduced cognitive load trying to understand what vector of string is doing, as long as you don't use vector of bool. Yes, that is the appropriate time to laugh. Just making sure everyone's awake. And the user can take advantage of this interface sameness, right, by writing a function template, right? They can write a function template that takes advantage of the fact that vector has the same member functions regardless of whether it's a vector of int or a vector of string, right? But this doesn't always have to be the case. The user can also write a function that is specific to a type, right? So if we go back to our animal example, we could have a vector of unique pointers to animals, right? And then loop over them, right? And we are still reusing the cognitive load of the vector container type, right? But we are not connecting that code in any interface sameness way. So if you squint at this, right, you're looking at like putting this function in your library is really including this handle disturbance function in the non-intrusive interface of vector of unique pointer of animal, right? So if that didn't make sense, then maybe it will in the next slide. But right, we're creating an interface, and and this function is not part of the interface of vector of int, right? So like the disturbance in the barnyard, there's no like meaningful thing to do for a vector of int, but for animals, we can have them all speak, right? And so in other words, we've introduced an interface difference while still maximizing implementation sameness. So when I first came across that way of expressing things, that kind of blew my mind, right? That separation, I think, is really important here. But usually how we express interfaces is intrusively, right? At least in the way that C++ is traditionally taught, right? We might have a class named Barnyard. We might also have a class named Canvas. Barnyard is a collection of animals, and a canvas is a collection of shapes, right? And in the case of Barnyard, well, we're going to handle disturbance. In the case of a canvas, then we're going to handle, you're going to calculate the total area, right? Those are completely unrelated things. Obviously should not be named the same thing, right? Because they do different things. Naming them the same thing would be bad, because then someone could write a template that takes both of them and does the same thing. And then what, right? Then those two pieces of things are coupled, right? So a question here, like I put this up on the slide and put this ... here, and like nobody probably was like, oh no, what's the ... I'm so confused, right? It's because you looked at this and you can pretty much fill in the ... in your brain, right? A type that is a collection of things for a purpose is going to have some kind of common functionality to it, right? In this case, conceptually, the ... is like, okay, we might have a function named insert. We might have a function named remove. We might have a contains. We might have a remove if, right? We're going to have some sort of functionality that addresses the fact that this is a collection. So how do we expose that sameness without repeating ourselves between these two types, right? We don't want to write insert in both of these types because that would be losing sameness, right? And this is often where people end up copy-pasting, right? And there's no way of knowing that, oh, if someone made a mistake in Barnyard, then you should definitely go look at Canvas to make sure that they didn't also make that same mistake or copy that same mistake over, right? So one way to do this, to expose the implementation sameness, would be to just have a way to get the vector, right? Now the user has a vector, and they can use the implementation sameness of vector and the interface sameness of vector directly, just by getting it, right? Now, anyone who is done software engineering for a very long time knows this is a really bad idea, right? Why is this bad? Can anyone shout out some reasons, like keywords as to why this is bad? Yeah, breaks encapsulation is one of the things I said. It leaks implementation details. It's not restrictive enough, right? If you're giving a non-const reference to someone, they can just go off and assign something to it, right? And it still doesn't even express all of the forms of sameness here, right? What is a form of sameness that's not expressed by this? Anyone have a thought? How about the fact that neither of these are inherently ordered? Right? A barnyard is a collection of things with no inherent ordering to it. A canvas is a collection of things with no inherent ordering to it. It's just in the particular case of how we are using it, it happens that the most efficient way to do so is with a vector, right? And so that leaks into that implicit assumption leaks into the interface, right? So let's talk about mixins. This is one of my favorite topics in all of C++. So we had this owning collection of things, right? We were talking about that in the previous slide as the kind of conceptual ... that's common between these two types. How do we usually spell of things in C++? I've actually done it several times in this talk, right? I've said vector of int, vector of string. We usually spell that with templates, right? So the most natural way to express like owning collection of things in a way that generalizes and in a way that expresses the sameness is to use a class template. This is, by the way, I don't know if any of you have ever worked on a code base where someone who doesn't, I'm okay with saying someone who doesn't know what they're doing, has tried to ban the use of templates altogether. Has anyone ever been on a code base like that? Yeah, right? You're going to get a lot of copy pasta, right? Because you're lacking one of the efficient tools that you need to express sameness. You're going to lose a lot of information as your code base evolves. So we could express the ... from the previous slides. Now I still have a ... here that's constructors, and I'm actually not going to go into why mixins don't address constructors very well, but that's another tangent. But basically, we've moved all of that functionality into some common place in the code without coupling these two types in any meaningful way, right? A barnyard is not related to a canvas in any meaningful way here. We have an owning collection of animal and an owning collection of shape, but neither of those are related to. Neither is a subclass or superclass. You can't cast one to the other, right? And we can put our common functionality here, and we've expressed that someone who has seen a barnyard before will probably know that, at least with respect to the owning collection part, it works similarly to a canvas. And that's really, really powerful. That's important that, 10 years in the future, someone can see the connection between those two types. And we can even do this with non-public functionality, right? We can have a protected function. And here, we have this sameness between these two, right? I had for loops here, right, over a data member, but really we don't need to make a private data member, or sorry, a protected data member here. Really, we can keep the data private. The thing that is common is the ability to iterate over these things, right? And so that doesn't necessarily need to be public functionality. Maybe that is too permissive for the interface that you're trying to describe. If it's not, you can always expose it to the user yourself, right? But the commonality between these two is that there is a way to iterate over that collection and do something, right? And so, yeah, so we succinctly express the implementation sameness between barnyard and canvas while introducing the minimal amount of interface sameness. So this is called a mixin, and other languages have different first-class mechanisms for expressing mixins. Unfortunately, in C++, inheritance works well enough that we just do it this way. In this case, we've introduced some interface sameness, like I said before, right? We've introduced these functions that allow our users to share the cognitive load, Although we can split the implementation, right? We can override these functions in the derived types. So we still maintain some control. It's just that every time the user says insert, they're going to do something, they're going to expect it to do something that is like inserting, right? And so these types aren't necessarily coupled in that sense, but we have coupled the user's cognitive load. So it is a cost to think about, but it's also a benefit to think about, right? And yeah, the reuse of names helps us to reduce cognitive load, but we can maintain some control. I really should read my own slides. Okay, let's talk more about sameness. We have two types here. This comes up a lot. Who's written a type like this before? There's another way of saying who's not asleep. Yeah, right? Like there's no dots here. This is like the whole type, right? And this is a common thing. And like one of the first things you might want to do is have equality comparison, right? And you might want to have not equals also, right? And et cetera, right? You might have all the other operators. You might not, depending on if it's an ordered type, not an ordered type, right? Same thing with bar. And I know a lot of you out there think you know where I'm going with this, and I am, but not the way you think I'm going there. Right, we have a type of sameness here. What type of sameness is not being expressed by having to write these things out? Anyone shout it out? It's element-wise comparison, right? That's a succinct way of saying what the sameness is here. Both of these types have element-wise comparison. And they have complete element-wise comparison, right? And so we can actually express that, right? If you look up like C++ mixin, this is usually the example that's given, right? So we can have this comparable element-wise for foo and comparable element-wise for bar, right? And then we can put in our implementations of equals, not equals, less than, greater than, right? This is curiously recurring template pattern, which if you've ever like talked to me for more than 30 seconds, you've probably heard me talk about. It's one of my favorite parts of C++ because it so succinctly and so clearly and so safely expresses sameness and without extra runtime cost. In this case, elements is sometimes called a customization point, right? It is a succinct way of expressing the differences that enable the expression of sameness. So we have isolated the part that is different about foo and bar to this one function named elements, right? And then we've isolated the part that's the same to this CRTP base class, right? And we can reuse customization points. This is a really subtle thing here that we're going to get into upsides and downsides of. But right, if we wanted to also print the type, right? If the type is printable, right? We could do the same thing here, right? We could make foo printable element-wise using the same customization point, because all we needed to do is get the members and print them one on each line, right? As long as each member implements the stream operator. Looking back at this, though, this implementation here, right? We have this static cast of derived const ref to star this dot elements. Now, does anyone, like, if you've ever used CRTP before, you've probably seen this, right? This is the weird way that you refer to the derived type that you need to work with here, right? And we can do this safely, right? Because we know that by construction, as long as you inherit this way, you're always going to be casting down this way, right? As long as you didn't copy and paste this from somewhere else and put the wrong type here. But you can make static assertions about that type being the same as derived, and there's ways around this, right? But anyway, you have so you have to do this weird, like, I don't know about you, that doesn't look like normal C++ code to me. Like static cast is already like, okay, what are we doing? So let's think about this. This common downcast that's part of CRTP. It's a common pattern. Can we say that common pattern with code? Can we express the sameness that is this downcast that gets reused? Well, yeah, this is the amazing thing about mixins that's impressive to me. You can express the sameness in the mechanism of sameness, right? You can express the sameness in this CRTP mechanism using a mixin, right? You could create a mixin that does the downcast and names that downcast self. And then when you mix that in with into your mixin, all you have to do is use self, right? I think that's incredible and says something about the power of the mechanism itself, that it can be used to express the sameness in uses of the mechanism. So many of you who are familiar with C++ 23 and are familiar with, have nerded out on this, are saying, but what about deducing this? You don't have to use CRTP anymore. The great thing about C++ 23 is you don't ever have to use CRTP again. Sorry to burst your bubble here. Hopefully, at some point, you'll, having seen the talk to this point, will understand where this is going and why this is a problem, right? So C++ 23 allows you to use this pattern here that deduces the type of this. And it uses this special syntax, this introducer with the keyword this, that causes the self parameter to have the type of the object that is calling the function, right? So this is actually being mixed in the same way that CRTP works, right? And self will be deduced to be foo. And then we can just use self here to get the elements customization point. We don't have to do a downcast. And this is great in many ways. And then we just inherit like this. We don't even have to put, you know, the of foo, printable element-wise of foo, or, you know, specializing foo, or however you want to say it, right? Can anyone say what's wrong with this? Anyone confident enough in what I've said so far in this talk to say what's wrong with this? No. Close. Static type versus dynamic type is very close to the problem, and it's a symptom of the problem, right? The problem here is that we've mixed interface sameness with implementation sameness, right? So what happens if we do this? Has anyone tried this in C++ 23? It looks like you should be able to do this, right? Everything we're used to in C++ makes us think we should be able to do this, right? Because print is inside of the curly braces here. So why can't I do this? And it's not, you know, equals 0, right? It's not virtual equals 0, right? Fortunately, this doesn't compile. It doesn't give you a runtime error or anything. But it doesn't compile for very confusing ways, right? And that's because you can write in your code printable element-wise without ever referring to foo. And that's a problem, right? So programming language designers often talk about two-sided names and the advantages of two-sided names, right? The fact that you have to write foo in here, and the fact that you have to write foo in here, in between this and the star, right, is actually an advantage here, right? It expresses in the code that everything in this vector has to be a foo. And that's actually an advantage. That's actually, even though it's more typing, it's a significant advantage of CRTP over using deducing this in this context. So what other forms of sameness do we have here? Can anyone point to one more form of sameness or repeating ourselves in this code snippet? Yeah. Exactly. Forward as tuple has the same list that we already have here, x, y, and z, right? We have x, y, and z, and x, y, and z. We've had to repeat ourselves, right? We've had to forego some implementation sameness because of the limitations of C++. And expressing this sort of sameness requires reflection in the general case. C++ badly needs reflection. I hope you're starting to be convinced of that if you weren't already. And it doesn't have to be good, right? If we can just like have any way at all to list off the names of the data members, then we saved ourselves a lot of headache here, right? So let's talk for a second about language support in C++ for mixins. In C++ 20, we got language support for one very specific type of mixin, and that's operator spaceship. And this is what I said earlier, by the way. Some of you probably know where I'm going, but it's going to take me a while to get there, right? Operator spaceship does all of the mixing in of the comparison operators from before as a language feature, right? But we're kind of adding reflection to C++ piecewise, right? I bet most of you, until you saw this slide, and if you hadn't seen this talk before, never thought of spaceship operator as a mixin, right? So we've introduced this thing that everyone has to think of as new and different, that really is a different version of something we already have, right? But we don't have any way to make that connection because we don't have the language level tools for generalized reflection. We can't express this, all aspects of this, in the language today, right? So we are adding cognitive load to the language in a way that's not sustainable. And that's a big problem. This is why we need reflection. Like, I think we're all clear on that at this point. Let's talk about another type of sameness. I think this is I'm going to go through this pretty quickly because there are lots of great talks on R-value references and qualifier forwarding, universal references. But it's as an example of something more broad that I want to talk about. So if you haven't seen this, there is a back to basics talk that Klaus can point me to right now. What is it? Is it the R-value reference one, or is it the forwarding talk? There is a forwarding reference talk at this conference in Back to Basics that talks about this more thoroughly. But the tref written exactly like that, or whatever name you choose for it, but the actual ref with nothing else, will create a universal reference or a forwarding reference. This has been around since C++ 11, and it's effectively equivalent to writing the same thing 2 times. So writing the L value version of this and writing the R value version of this, because we decided to use the same syntax for a forwarding reference and for an R value reference. It's actually really hard to write the R value version of this, but you can do something like this, create a alias template that does nothing, and then have that, and that will be an R value reference all the time, and not a forwarding reference. But the point is that there is a sameness of function body, right, that is expressed by this qualifier forwarding here. Now, qualifier forwarding on member functions is actually a little harder. And let's talk about why. I showed this earlier, right? We talked about this for each that was expressing sameness in our mixin. But there's something missing here. Does anyone know where I'm going with this? What's missing? I'll give you a hint. Right? There is a non-const overload missing, right? And these 2 functions are probably implemented basically the same way. And actually, if we want to be thorough, it's more than that, right? We can have reference qualified methods, right, with L value, a const L value, an R value. If you want to be pedantic, you can have const R value, although that's not really very meaningful in C++. You can have volatile, const volatile, etc. I'm assuming that you're a good person and don't use volatile. But the problem is, even with just these 3, right, we already have to repeat ourselves 3 times. And there's no way for the reader of the code, other than through convention, other than through training, to know that all 3 of these ... dots are the same. You can run diff, right? But that's really not a good way to write code. So C++ 23, deducing this is actually an amazing thing that C++ 23 gave us with deducing this, allows us to deduce a forwarding reference, right? Remember the tref thing? we can deduce a forwarding reference to the type that is calling that for each is a member of, right? And use perfect forwarding, right? And that actually makes all three of these be expressible as one thing. And that's actually really powerful. Taking this one step further, though, if we have a bunch of things like this, right? You've probably seen this in code before, right? Where you have a function that just calls the same function on a data member, right? This is, in other languages, this is often called name forwarding or delegation pattern, or two kind of keywords you could look up on this. And C++ doesn't have this. We tried for about a decade to get operator dot to customization to work, and some versions of that would have given us this. Reflection would obviously give us this. And we can even have cases where like the better name defers to a different name, right? That's another version of this same thing, right? This is a straw man syntax. I'm not creating a proposal, C++ proposal, but, and just for fun, I mixed like Ruby and Python ways of doing this, so yay. But like something like this would express the fact that clear, size, swap, etc., all just forward to things, right? And insert forwards to the pushback on things. Right? This is the same thing as reference forwarding, but taken one step further out, right? We just want to say that this is doing the same thing on that. And why is this better than exposing vector directly to the user? Why is this better than returning a reference to the vector? Well, it's because we still maintain control over this interface, right? We can, at any time in the future, go write a different clear that does something else, right? We can go write a different size that does something else. We haven't exposed the fact that this thing is a vector to the user, but we have expressed to the reader that it acts, that this function acts like a vector in this way. So that it makes the code much more readable without exposing us to implementation, to interface sameness and code coupling. This would be pretty easy to build on top of basic reflection. In fact, in both Ruby and Python, this is a library feature. A number of other languages implement this as a library feature, right? It is a reflection-based library feature, but it can, or reification-based, right? Depending on how you want to see it. But it reuses understanding. It allows us to propagate code changes, right? If I were to have different overloads of insert, I can propagate those different overloads back up through the things that use vector, right? So there's some upsides and downsides to that, and how you want to actually introduce name forwarding into the language has to be done with thinking about that. But this is another type of sameness, and it's actually a mechanism missing from C++. So in general, I've been going over this don't repeat yourself, and I have 14 minutes left. All right, let's see what I actually want to do with this. Sure, I'm going to go through this very quickly, and if you don't understand it, then probably go back to the section of this talk in my core C++ talk in Israel. So don't repeat yourself is this principle that every piece of knowledge must have a single, unambiguous, authoritative representation within a system, right? This is what we've been getting at this whole time, right? So let's talk about what every piece of knowledge means here and how we can apply that to maybe think more about this. From this earlier example, owning collection of things. What are the pieces of knowledge here, right? We have ownership and we have a collection. So maybe we could start looking at how do we split those two out, right? Maybe this is the way that we find more expression of sameness. So we could say, oh, why don't we be generic over what kind of owner we have, right? And this is a typical pattern for a class template customization point. We have these in the standard library. I'll get to them in a second. What else could owner be here, right? Owner could be a shared pointer. It could be a small buffer optimization. This can be taken too far very easily. I'm going to show in a second a case where like a bunch of very smart people on the C++ committee got this wrong, myself included. And a good customization point takes a career to learn, really. And even then, it's like we're lucky to understand it at that point. So if we look at the standard library, things like vector, right? This is a class template parameter customization point, right? It separates out the idea of contiguous storage, which is an expanding container with contiguous storage, like vector, from how that storage is created and destroyed, right? And we can go one step further, one layer of abstraction further. std_q separates out the semantics of a queue from the container that it uses to implement those semantics, right? It's a layering of customization points actually here, right? Because dec has an allocator, right? And so we've layered customization points. There's quite a lot of complexity in that one thing that's usually just written std_q of t. So here's another one that we can talk about. Unique pointer of deleter. Can anyone who wasn't in my talk in Israel, hang on, let me get to that in a second. So right, we have this separable piece of information of how the object is created or destroyed, which is separable from the idea of unique ownership, right? Where is the allocation portion of this customization? Does anyone know? In the constructor, right? It's transient. We don't actually need to carry the allocation mechanism with the type because it happens once at the beginning of the lifetime of the type, right? And we only need the destruction, which can persist across different uses of the type, right? And so if we were wanting to use a unique pointer with a stack allocated data, right? We could give this like empty destructor, right? And pass it on. And there are valid reasons to do this. But yeah, I won't go into that right now. Usually you're going to use make unique, right? Let's go down the rabbit hole. Can anyone who was not in my talk in Israel tell me what's off here? The design isolates the piece of knowledge that needed to persist for the lifetime of the object. Well, sort of. I'm going to skip that. The deleter also has some information on it. But more importantly, are allocation and destruction actually separable pieces of knowledge? Like, did we go too far here? Like, how many people know of a deleter that can function in general without knowing how something was allocated? We get away with it because the most common way of doing this is new and delete. But we've separated things that really aren't fundamentally separable, right? So where did we get separable from? Well, we got separable because it was like we were trying to be more generic in the abstract without having a motivating use case for it, right? We started looking and we were like, oh my gosh, there's single, unique, single, unambiguous, authoritative. There's pieces of knowledge that need a single, unambiguous, authoritative information, and I see two different pieces of knowledge here. Let me separate them, right? And that's where we went wrong here. So, like, when you're stuck on something like this that looks wrong or something feels wrong, you can look at analogous situations. Well, why? Because it reduces cognitive load for the user, but it also allows you to not repeat yourself, which is really powerful. As we've been showing, it allows implementation sameness sometimes, right? What is the most analogous case in the standard library? It is shared pointer. And if you read on CppReference.org, which is generally pretty good about these things, it says, and it is here also, every standard library component that needs to allocate or release storage from std_string to std_vector to ... shared pointer does so through an allocator. So allocating and releasing are not separable pieces of knowledge from the standard library's perspective. And the authoritative representation for allocation and destruction is the allocator abstraction. So let's look at unique pointer. So unique pointer is broken, right? Like we don't use the authoritative representation for allocation instruction. Fortunately, shared pointer uses allocators, so this is a constructor of shared pointer. It takes a deleter and an allocator. Does anyone have any clue why we would do that? Okay, these are used separately. Does anyone know which one's actually used to destroy the data off the top of your head? The deleter, that is true. I can't come up with a first principles reason why that's the case, other than looking at the documentation. In fact, I would think an allocator, well, I don't know exactly. The alloc.destroy is used, but not how you think it's used. It's used for the control block of the shared pointer, which is weird. So fortunately, we standardized allocate shared. And allocate shared does take an allocator, and it uses it for both allocation and destruction. It's fantastic. World fixed, right? So there's an easy way to be consistent, right? We use make shared when you have no allocation or deletion customization, and use allocate shared when you need to customize either of those. And if you're using the shared pointer constructor that takes both a deleter and an allocator, you're probably doing something wrong or doing something so obscure that you probably shouldn't be doing it. So why not allocate unique? So this is the interesting thing. I was putting together this talk, and I was like, oh, unique pointer is a great example of customization point design, and we can talk about how it's good about reusing code. And then I was like, wait, it's broken. And so then I put together all these slides, and then I looked at the paper for allocate shared, and I was like, why didn't we also do allocate unique? And in that paper, STL, this is like a pre-P number paper. This is an N number paper. But it's actually a fantastic read from the perspective of this talk, with the perspective of this talk in it. And the problem that we ran into that we trying to make allocate unique is the fact that this isn't an allocator, right? And there's no way to translate between an allocator in the standard library. There's no way to translate between an allocator and deleter. So we'd have to return unspecified, or we'd have to add a adapter to the standard library so that people can spell the type that comes out of transforming an allocator into a deleter. And furthermore, one of the possible suggestions for a path forward, which STL doesn't recommend, and I agree, is to just say, well, let's pretend we got this right. And if there's no call operator, then we treat it as an allocator. So to me, this was really validating of my reasoning, to look at it and be like, wow, yeah, we did actually get this wrong, right? Anyway, into the unique pointer rabbit hole, I'm going to talk about the elephant in the room very quickly. I did a much better job of this in Israel, where I had more time. Where do concepts fit into interface and implementation sameness? C++20 concepts extract interface sameness without your permission and are extremely dangerous because of this. I could give a whole talk on this, and probably should. And actually, Titus's talk from 2022 at CppCon, one of those two, talks about this and why it's so dangerous, right? Concepts allow library users to accidentally create coupling for your code coupling based solely on names of functions in your type, right? So if I have a container and a color, and my container wants to return whether it was non-empty before, so it has a bool clear. And I have a color that has opacity equals 0, returns clear. These two types are now accidentally coupled. Because we can write requires t.clear. This is one of the main reasons why requires is an anti-pattern. If you ever see this, this is the assembly code of concepts. You should use named concepts at the very least, right? But this is going to be very confusing. It can pop up the moment you add this library. This ambiguity can pop up the moment you add this library, right? Because what if you have a container of colors, right? So now you have this function incorporating both namespaces from an ADL perspective. So also don't use ADL. But And if you don't know what ADL is, also a good thing. Argument dependent lookup. Good rabbit hole to go down. You will probably not want to use C++ after that. But yeah, concepts don't check namespaces, right? Concepts don't respect namespaces. This is a really big problem with concepts. And I don't think there's good news here, right? I think the news here is that like you should be very careful when using concepts. And like use named concepts, be very, sparse in the concepts you use. Don't allow people to accidentally introduce interface sameness without your permission, because you can't claw that back, right? Once somebody has treated something as the same, you can't claw that back. You have to support it in your library for the rest of eternity. And that's a really big problem with concepts. So there are so many other things I wanted to put into this talk. Maybe I'll do a version 2. Normal functions, macros and code generation. Sometimes that's the best way to express sameness. It's better than copy pasting because at least it creates a connection that people can figure out later. Customization point objects, type erasure, const expr functions have this kind of sameness between compile time and runtime implementations. I talked about that a little bit in my C++ North talk from last year, 2022. But it is a kind of sameness, right? Dependency injection, which really, really would be nice to have in C++, but we need reflection for it. Aspect-oriented programming, another thing that we need reflection for. Decoration, another thing that we need reflection for. You get the idea. Reflection would be really nice and would really improve the code quality of large-scale software engineering in C++. Questions? Oh, that's the wrong link. But yes, it's down here. The right link is down here. CppCon 2023. Does anyone have any questions? I think I have 44 seconds, and I started 3 minutes late, so I'm going to go 3 minutes and 44 seconds of questions. Is that OK? Go ahead.
Thank you for the talk. I have a question. What's your thoughts or opinion on unified function call syntax in C++? Will it help expressing sameness or rather make things worse?
I had a feeling that question was going to come up. It didn't come up last time I gave this talk, so I was like, maybe I got around it. No, I mean, unified function call syntax and operator dot have many of the same problems. I think it allows some sameness, but it also allows some dangerous sameness. Right? So it has some of the, you lose some of the ability to control the way your code is used, because you can end up with accidental collisions that you didn't think about before. But at the same time, it does allow expression of sameness when two things are similar enough. I think right now, customization point objects or nebloids are probably the way that we're getting to that same effect. They're gross. But if you're writing a library that is generic enough that you need universal function call syntax for things that you customize, then probably you should go through the grossness. I don't think generally you should be that generic, unless you're writing the standard library, or like abseil, or like STLAB, or something that is going to be used quite broadly. So generally, if you don't know how to write an ebloid, if you've never heard of an ebloid, you shouldn't be writing them. But they do emulate universal function call syntax in a sense, in a vague sense.
Thank you. Another question: what's the rule of thumb on where should we go? How deep we should go by expressing sameness? For instance, like for me, expressing the sameness of static cast was a bit too far.
Yeah, there is there is a rule of thumb, and it is what will improve the readability of your code. Right? And there's no substitute for that. You've got to talk to your users. You've got to sit down and code with your users. You've got to read their code. You've got to see what they actually understand. Knowing the people on your team, like so much of software engineering is about people. And that's so much more true today than it was 10 years ago, than it was 20 years ago, and it's going to be more true 10 years from now. So it's just about knowing the people and knowing what's going to be most readable to them.
Thank you.
Mm-hmm.
Thanks so much for the talk. It was very interesting. So a quick question about the deducing this example. I actually had not heard of that interplay with CRTP. That's very interesting. You said that the error that you get, is it that like it's a non-deducible context, or is it that it deduces the wrong thing and it can't find the function? I was just kind of curious.
The errors are getting better and evolving very quickly. I have not checked in the past 6 months. The ideal error there would be something like, you know, last time I checked, it was like template can't be instantiated, which
okay,
I don't think most
I was
people are
hoping.
Gonna, yeah, know that. But it hopefully is starting to get better.
Thank you.
Hi, thanks for the talk, obviously. It was really great. So I kind of have two questions. Well, one's a question, and the other one is either a question or a comment, depending on the answer to the first. So my first question is, it's pretty common, at least in projects that I've worked on, to use inheritance, specifically private inheritance, to express some amount of sameness of like, hey, you know, I'm going to inherit from std vector, but I'm going to do it privately, so I can't convert to this thing, but I want to use the majority of its interface. So, you know, you inject a whole bunch of using declarations to do that. Is that a pretty good mechanism to express sameness?
Yes, I think actually the thinking on this is evolving, and it's evolved a lot in the past 10 years. If you look at C++ books from like 2011 or 2012, they will say absolutely categorically don't ever do this. I think that people's thinking is evolving, and the way people use C++ is evolving to the point where that makes a lot of sense. It is a version of name forwarding. Be careful with it. Make sure it's private. Don't let people treat your type as a vector reference.
Yes, which also brings me now to the question, the second question, which is that deducing this is a good way of eliminating a lot of the you know, the CV qualifiers on the this type and duplicating your functions all over the place. But with that method that you presented is really interesting when you have private inheritance, because now your derived object could use that deducing this function. And if that deducing this function uses any private stuff from the base class, now you've broken that for the derived class. Because when you use that with the derived class, you're going to get the derived type, which doesn't have access to the base class members. So it's kind of like an interesting breakage that happens. I'm not sure if
I'm not actually sure if that's true. I don't think you can say self. No, you can. That is true. Yes, although I think this is a problem that normal inheritance also has. There's a much longer answer to this that I would love to give, but I actually want to hear some of the other questions, and I'm happy to talk about this offline.
Yeah. Thank you.
Thanks.
Hey, thank you. Great talk. But I was thinking if we take expressing similarity to the extreme, then we may end up with mixins, like a chain of like tens of mixins inheriting one from each other.
Yep.
And like adding one or two methods. And I've actually seen such code.
I have too. It's
Do you
beautiful.
think this is good for readability, and what could be the solution?
So there are cases where the complexity of the problem at hand actually demands that. If you look at the standard library implementation of variant, for instance, in libc++, I believe that was Louis Dion. Someone can correct me if I'm wrong. It is the most elegant expression of all of the weirdness that you have to do with constructors and destructors and everything else in order to compose std variant in a library context.
Yeah, to support like trivial constructs.
Right. But don't do that if your problem is not that complex, right? I mean, we showed an example of how we are trying to derive sameness from separation rather than from actual need to express sameness, and how that can go wrong. And I'll take this last question. I know the session is over. Feel free to leave. You can check out the question on YouTube or something.
Yep, thanks so much. I'm just wondering, like with the barnyard example, is there a point where your class is so much the same as a standard vector of a thing that you just give up on the like abstraction and say, this is just a vector of animals and we don't need?
No, I disagree with that. Like names have power and names are very important. And even if you're literally forwarding everything to a member, the fact that you're telling your user to think of this thing as a barnyard and think of it that way every time is still incredibly powerful even in that context. And it doesn't cost you anything, right? It doesn't cost you anything from a runtime perspective for the most part, right?
Thank you.
Thanks. Thanks, everyone.